Questions? Yes.
Do you want to finish reviewing the pretest?
Yes. Also, I'll hopefully have the time to talk about section 1, just to get you started. It's really not really that much more complicated. A bunch of the stuff that are in section 1, they are supposed to be reviewed, which basically means that you pretty much were tested on those in the pretest. So we kind of seen them a little more. Like, for instance, difference quotients would be one of them. I was hoping I was going to have the pretests done, and that did not happen. I'm done with, I guess, whatever the percentage that would be. Probably about 70% of the class. But just so to give you an understanding of why I'm taking so long, I actually have to go through every single problem for every single student, figure out if you did it wrong, if you did it right, if you did part of it right, part of it wrong, or anything like that. So anyway, the only thing, if you do have a particular question as to, if you want, as I said before, after class I actually have office hours, so if you want to actually see what your situation is at, if you're one of the lucky people that I actually did it for, I can tell you, a lot easier. If not, you probably have to give me about 3 minutes or so to actually come up with all the stuff for your situation. What I decided I'm going to do as far as the pretest is concerned, besides the actual partial credit that you might actually get, I took out problems 9, 10, 12, 24, 25, and everything past 31. And of course that doesn't necessarily mean much to you, right? Let me put it this way. 9 through 12 was the difference quotients. And I figured there's really no point in testing you on 5 different ones. I know 12 was a very popular one as far as not getting it right, and so that was one of the first ones that I figured I should take out. And then there were 3 of them involving quadratic functions, and I figured, well, really, do we really need to test all 3 of them? So I basically just dropped 2 of them and I just kept 1. And so basically, instead of 5 difference quotients, now you only have 2. Now, if you're one of the fortunate people that actually did all 5 of them wrong, then I guess technically that's penalizing you a little bit. If not, and you're among many people that actually haven't done any of them correct, then you're really favored, because instead of actually getting 5 problems wrong, you're only looking at 2 problems wrong. You had a question? Not necessarily. I'll tell you this. If by any chance your score is actually lower than originally, I will take that into account. If you look at problems, for instance, 24 and 25, which were the 2 trigonometric expressions, you were supposed to write one in terms of sine or cosine and the other one in terms of tangent or cotangent. I took both of them out because I think the wording was a little misleading, and again, those are very popular in the sense that for number 24 up to now, and I looked at 35 of the 50 exams, so it's kind of a large pool of exams, I think, that you can kind of get the information as where things are standing. So out of 35 exams that I looked at, there were 5 people that got problem 24 correct, and there was 1 that got 25 correct, and I gave partial credit to 2 other people. So I am really doubting that taking those out is actually going to hurt anybody. And as I told you from the get-go, the last problems, again, problems 31 and 32 were, I guess, popular in the sense that there were 7 people out of 35 that got it right, and 8 out of 35 that got it right. Okay, so that basically kind of comes back to having 25 questions instead of 34, and Just to give you an idea about where you might necessarily be, it's not that easy. As for instance, you can basically, I guess, go to online and look at your test and say, okay, if I take all those problems out, what my grade would be. But that's might not necessarily be accurate, because, for instance, as an example, and I only did actually one person, I only had time to actually add all the scores for one particular person. I'm still trying to figure out all of this. And that particular person going into the test scored 9%, which means he or she had, I think, 8 problems correct, or 7 problems correct, something like that. After the little, after me going through every single problem in the test, it came out that I basically am giving the person 12 correct instead of 8 correct, which basically originally was like a 24%. Now it's basically looking at close to 50%. And so that's more or less kind of the situation. I wouldn't really expect, if you scored in the 20s and 30s, I wouldn't necessarily expect that you're going to end up with a 70 or 80% when it's all said and done, just because there's really nothing really out there to come out with that much. So anyway, let's see. Questions? Okay, so now going back to what we were looking at, so I guess maybe I should probably pull that out. I think we were looking at like problem like 16 at that point, right? I guess you're, as I said, if you want to know what the situation would be afterwards, you can probably come to my office afterwards and we can discuss. And you are kind of the lucky group, because I think I said, I told you that I'm actually teaching 2 sections of 135 this semester. I haven't really gotten a chance to do pretty much anything as far as the second section is concerned, as far as the tests. So at least I actually have much more of a discussion about this with you guys. Okay, did we look at 16? What was the last one we looked at? 15? Okay. So let me see if I can turn this laptop around. I think the entire supply office decided to come and dump markers here. You think I'm joking?
You're a bucket or something.
I don't think I've seen so many markers at one point in one time. Okay, so let's see if I can do this now without actually getting all the lights flickering and all the other fun stuff going. I'm trying to turn it around, so we'll see if it actually works. So far so good. Okay, so problem 16. Is there anything we need to talk about in here? So the idea was, I guess let me just backtrack for 1 second. 15 was the first introduction with, so what was it, 13 and 14 dealt with exponential functions. 15 and 16 dealt with logarithmic functions, and the idea was 15 was to identify the graph of the logarithmic function, and you had 8 choices. I guess you could flip a coin 4 times, but the key idea is that they're all a variation, and so basically what you have to identify here, what you have to actually recognize here is the fact that they're all basically some variation on log base 2 of x. And so you have to recognize what happens when you put in a minus inside, what happens when you put in a minus outside, what happens when you add 1 to it, or things of this nature. And I know we kind of talked about this in the last time. Is there any point in talking about it more? Yes.
Could you say what the negatives do again? Like which axis comes over?
Okay. Well, first of all, what is the domain and what is the range of logarithmic functions? Because I guess to some extent that's going to be the next slide anyway, or the next problem. But that kind of would give you an understanding more about what's happening here. And so these two problems are kind of connected to each other. So I'm going to choose to go to f of x equals ln of x, just because it's less things to write. I'm hoping everybody remembers that ln of x is just log base e of x, right? So what is the graph of ln of x? And the answer is, this is the graph, right? Everybody remembers this? As I said, this was basically the whole idea. The whole idea is to remember what these are. And so, if this is the graph, what do we have to recognize? First of all, notice that x equals 0 is a vertical asymptote, right? Why? Well, ln's are defined that you cannot actually put negative numbers inside them. Actually, you can't even put 0. So, if I come back here, what is the domain of f? 0 to positive infinity, open at 0. Does that make sense? Again, you can see it from the picture, especially considering I just said 0 is a vertical asymptote, right? What is the range? Everything, right? Again, it's self-explanatory. The range is for all the values of y for which the graph exists, and as you can see, that happens for all of them, right? Okay? So now if I come back here, okay, I'm coming back in the wrong spot. Okay, if I come back here, bless you, log base 2 of x is going to look like this, right? What happens when I look at log base 2 of minus x? Well, I mean, I can easily tell you what happens when you put in a minus inside or what you put in a minus outside, but let's just think for a second, besides actually me just telling you what's going to happen. Before there, when we looked at log base 2 of x, we said it only works for all positive values of x, right? Because you can't put negative numbers inside here, right? That being said, minus x, if x is positive, is going to be negative, which means it doesn't make any sense. But if when x is negative, this is positive. As a consequence, the minus x is going to flip it over the y-axis. Does that make sense? Everybody understands why that's the case? Right? Because if you think about back to what I was having here, right? The domain now, instead of being 0 to plus infinity, is going to be minus infinity to 0. Right? Because I have a minus, which means I have to make them positive, which means I can't be on this side anymore, I have to be on this side. But everything else follows. The only difference is the positive changes to a minus, and so it'll just basically flip over. Does that make sense? On the same token, what do you think happens when I look at a minus outside of it? So let's look at, for instance, a minus log base 2 of x. Well, just think about what it means. For every value of log base 2 of x, instead of being at that point, I'm at the negative of that point. Which means instead of being here, I'm up there, and vice versa. Which means the minus in front is going to flip it over the x-axis. Does that make sense? So now with these tools in hand, what can we observe? Well, first of all, we're on the left-hand side. That should immediately raise a flag as to the fact that I need to have a minus inside. Right? Does that make sense? We just talked about the fact that it'll flip over. Moreover, instead of actually being an increasing, instead of actually starting from here going up, we're actually having the exact opposite direction, which means I'm looking at minus log base 2 of minus x, right? Now there's all of these with minus 1 inside and out, and inside again. Would those play a role? And the idea is, again, logs, by definition, you can't put 0 inside them. this is where the vertical asymptote comes into play. That'll tell us that none of B can't be a choice, C can't be a choice. Does that make sense? Do you understand why that's the case? Oh, no? Well, again, keep in mind, log base 2 of x, right, has the graph. It starts here, it goes up, which means at 0, you can't put 0 in for it, and that gives you your vertical asymptote, right? But what happens when I put 0 in here for x? I get -1. This doesn't make any sense. If I put in 1 for x, is what my vertical asymptote is going to be. Similarly, when I put 1 for x, is going to be where my vertical asymptote is, not at 0. And then as a last resort, can this be the 1? Well, what happens when I add or I subtract 1 outside of my function? It shifts up or shifts down, right? Because it's negative, it shifts down. How do I know that this is not shifted? Because ln of 1 is always 0. In our case, ln of -1 is always 0, right? Think about back to the graph here that I drew. The only number that I put on this picture is 1. Right? Why? Because remember what ln of x, y equals ln of x, is equivalent to saying e to the y is equal to x. Well, e to the 0 is 1, which means that ln of 1 is in fact 0. That's going to be your x-intercept. Is that making sense? Alright, so now with all of these tools at hand, we should have a much easier time dealing with 16. Why should we have a much easier time dealing with 16? Use transformations to graph the graph of ln of x plus 2. Right? Well, we can first look at the domain. Do you understand why the domain is -2 to infinity? Is everybody understanding that? Yeah? The point is you can't put negative numbers in there. Moreover, you can't even put 0, right? So it has to be strictly positive, which means x plus 2 has to be greater than 0, which means x is greater than -2. Right? Which means that. How about the graph? Well, what has to happen? Think about what happens when you put in 0 for x. Sorry. Wrong statement. What happens? How can I make the parenthesis 0? By making x -2, right? That means x equals -2 is a vertical asymptote. So when I look at my pictures, which ones I can cross out? A and C, because the vertical asymptotes actually go through on the positive side. I don't even know what the values are, or I don't necessarily care that on the positive side. I know my asymptote is -2, right? So now I'm left with, what am I left with? B and D. Do you understand why it's not D? Can you tell me what function is this? Close. It is, let me write it here. For D, I guess 16D would be y equals ln of -x minus 2. Do you understand why? Remember, minuses on the inside will move me on the other side, right? I still have an asymptote at -2, which means the quantity inside my ln still has to be 0 at -2, and so it will be -x minus 2. Does that make sense? Okay. Range of ln. Well, I don't care what I'm putting inside here. The range of ln is still going to be plus infinity to minus infinity to plus infinity. Does that make sense? I'm still going to start all the way from the bottom, go all the way to the top. The vertical asymptote, well, we just talked about it, so I don't think I need to spend more time on it. Is that making sense? See, the irony of this is, if I were personally to actually write this problem up, I would actually probably start off with what is the domain, what is the range, what is the vertical asymptote, then what is the graph. Because when I actually described which graph this was, I pretty much told you about this and we talked about that. Right? Does that make sense? Okay. Questions? Okay. 17. On Monday we actually talked about the way you write domains, right? And I told you this is basically a very acceptable answer. Otherwise, if you want to write it in interval notation, you can, or you can write it in words, all real numbers except x equals -7 and x equals 7, right? The one thing that I told you not to write was what? Remember what I said? That would not be a good answer. Do you understand why?
Because you're saying it can equal anything else.
I'm not saying it can equal anything else. The only thing I'm saying here is that x can't be -7 or x can't be 7. Am I automatically implying that it can be equal to anything else? You think so? Well, there's nowhere written there.
So that's what the x given x is for.
That's where, if you write it in set builder notation, that's actually what it says. This basically says, this right here means you're looking at all the x's with the property that x cannot equal -7 or 7. Or you can actually, I don't necessarily care if you do that, you can actually say it in words, all real numbers except, so and so. Or real numbers, that do not satisfy that criterion or whatever. The point is, you want to make sure you're actually being clear about what you're actually meaning. And the reason why this is something that we want to stress is the fact that if you look at this problem, I can just look at on top of the of this, and I can just say x is equal to x cannot equal 7 because that's the point. I can even say that x equals cannot equal -7 because I see those two in the denominator. But how about if I actually look at, for instance, let's say my function is h of x is square root of x divided by x minus 7, x plus 7. Well, I can easily say, just by looking at the denominator, that x cannot equal 7, x cannot equal -7. Right? But there's more. How do I know when I actually have the right answer? And so the point is, this is basically what I'm trying to say is, all I'm saying here is that x cannot equal -7 or x cannot equal 7. Do I mean that it can be equal anything else? Well, not really. The only mathematical statement that I'm making is it can't be these two values. As it turns out, what's the domain of this function?
0 to 0.
0 to 7, union 7 to plus infinity, you say? The domain for square root of x is 0 to plus infinity. But I have the 7 that I have to take into account. Right? Because if I put in 7, the denominator doesn't make any sense. Is that making sense? Okay. We're going to talk a little more about domains today if I actually get to them. Questions? Okay. Should I spend any time on the 18? I think the majority of the class actually got this right. Or close to being right. For some reason, I've seen a lot of papers in which there was a open parenthesis at 4, or whatever the situation may be. That actually ends up being the vertex, and that always actually is part of the function, of the range. So, should I spend time on this, or should I just move on? We talked about quadratic functions, we talked about x-intercepts, y-intercepts, right? Okay? 19. Okay. 19, 20, 21 dealt with trigonometric functions. And this is when things got very hairy. So, as I said, let me repeat myself. Trigonometric functions are going to be a very important part of our class from this point on. So, you have to basically, as we were talking about it at some point in the past, you have to be kind of your own critic here and realize that if you actually haven't gotten any single trigonometric problem correct, is it because you just haven't seen them in a while? Is it because you're not really understanding them? Or why exactly is the purpose? Because if it's that you're not really understanding them, then you really need to take pre-calculus to understand trigonometric functions. If it is just the fact that you haven't had them in a while and you kind of confuse the fact that sine of pi over 6 is pi over 6 is 30 degrees. That's not a question I asked. I said, what is sine of pi over 6? 1/2. So if you don't remember it's 1/2, and you remember, by accident you said that it's square root of 3 over 2, or whatever the situation may be, then it's something that can be easily rectified. Now, if I just said sine of pi over 6 and you have no idea basically what I'm saying, then again, that basically should tell you that you need to go back and make sure you take trigonometric functions more seriously, because I know you probably don't necessarily like them that much, but trust me, there is no getting away from them, ever. And I don't know, how many of you are science majors in any shape or form? Okay, for all of you that are science majors, trust me, when you get into the real world, in whatever science you're taking, trigonometric functions are going to be a very important part of your lives. You can't get away from them. The simplest and most common example you can think of, and I basically say this out loud just in general, just to give a simple example, is, let's say you go by the beach one day and you decide to take a rock and throw it in the water. As the waves move, those are basically all governed by trigonometric functions. That's why they look like that. Think about, like you go and want to take a hot bath and you turn on the water to collect water. As the water drips, you start getting ripples. Those are all governed by trigonometric functions. Now, I'm not saying you're actually going to have to derive those at any given point, but you will see some variation of that at some point in it, because this is basically the science that surrounds us. And it might be, obviously that's an example of physics, but you can have the same example in chemistry, biology, or any other major you can think of. The whole point is, life is cyclical. The only functions that we know that are cyclic are periodic functions, which means sine, cosine, tangent. Well, I'm just giving the three. Do you have a question?
Yes. Would you be able to draw a unit circle and just talk about that for a couple?
Yes, I will. So, trigonometry. As I said, probably one of your favorite topics. Let's see. Let's do it in what? Should we do it in two different ways? First of all, let's say I have this lovely axis system. That's theta. And so the question is, based on this picture, what is sine of theta? What is cosine of theta? What is tangent of theta? So let's name this R over here. I'm cheating. This is actually I guess maybe a little more than we need at this point, but nonetheless, I'm just naming them something. So what is sine of theta? What is it? Y over R? What is cosine of theta? And what is tangent of theta? Now, you probably see me that I won't really be doing this. I'm only actually concerned in general with sine and cosine. Why am I usually only concerned with sine and cosine? Well, tangent of theta is nothing else but sine of theta over cosine of theta. Cotangent of theta is cosine of theta over sine of theta. Secant of theta is one over sine of theta. And cosecant of theta is 1 over, 1 over cosine of theta. That's, hey, somebody's awake. And cosecant is 1 over sine of theta. Does that make any sense? Okay. All the notice, and this is actually going to be a pattern that's going to be repeated as we go through this class. Or I'm going to say this a few more times later on. Notice that 3 of the trigonometric functions do not start with a C. 3 of them do start with a C. The 3 that start with a C are called cofunctions. And we will see later on what properties cofunctions have and why we actually talk about them. There's usually a way to relate a function with its cofunction. Like for instance sine and cosine, tangent and cotangent, and so forth. And a very simple way of relating that is can you tell me what's the relationship between, let's see, what do I want? I guess it doesn't really matter. Sine of theta and cosine of theta plus pi over 2. Sorry? They are equal to each other. That's why they're called cofunctions, because one is actually just a shift of the other in the end. Does that make sense? Okay. Now, the lovely trigonometric circle. What do we do here on the trigonometric circle? First of all, if I am to just put the values at the for intercept, this will basically tell me that I'm dealing with a trigonometric circle, right? If this is an angle theta, what can I say about this particular point over here? Do you remember how we set things up, or not really? Not really? That's how the trigonometric circle works. Any point x and y will have coordinates cosine of theta and sine of theta. Okay? One easy way of remembering which one is which, because I might sometimes forget, is that one of the things that I always remember is that sine of 0 is 0. And from that point on, everything else kind of spans. So, I usually know that sine of 0 is equal to 0. Now, because sine and cosine are cofunctions, I know that if sine is 0, then cosine better be either 1 or minus 1. Well, in this case, it's going to be 1. Does that make sense? Okay, so we have to remember, in general, they're so common that we usually have to remember 5 angles. 0, pi over 6, pi over 4, pi over 3, and pi over 2. these five trigonometric angles, and by the way, remember what I said on Wednesday, and I'll repeat it again. I think I said it on Wednesday, or I'm losing my marbles and I said it in the other calculus class. For the duration of the semester, and from this point on, regardless if you just need to take Calc 1 or need to take Calc 1, 2, and 3 or any other thing, in general, whenever we're going to be dealing with angles, we will always refer to the angles as in radians and not degrees. And so, notice I wrote them in radians and I did not write them in degrees. And we're not necessarily going to be concerned with how many degrees is, pi over 3 or anything like that. Okay? The whole point is we want to talk about them as being real valued functions, and so we're going to always talk about them in terms of radians. Yes?
Why is there a preference for radians?
Why? Because again, as I just said right now, we want to view f of x equals sine of x as being a real valued function. Real valued functions, the domain of this function is all real numbers, right? Now, do you know how degrees work? What are the divisions of degrees? You're looking at degrees. If I say degrees can go up to from 0 to 360, right, as far as the circle is concerned. What is the next division of degrees? So, for instance, if you are actually on a boat in the middle of the Atlantic Ocean and somebody asks you, what's the longitude and latitude? What do you tell them? You tell them the degrees, you tell them the minutes, and you tell them the seconds. That's how it works. Well, 60 minutes form a degree. 60 seconds form a minute. The real system that we're actually working with is a decimal system, which means it doesn't get divided by 60, it gets divided by 100. And so you can't really be plotting a function in degrees, considering your real axes are actually defined in real numbers, which means they're defined in radians. That's why we always use radians, because the idea is you write 1.537 blah 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 radians, which would be a certain number of degrees, but the point is you can use any real number to describe it. Okay? Technically you have thousands of a second, but that's still not good enough, because again the point is you get to minutes and seconds, and then you get to thousands of a second, and so there's all these weird confusions, right? I mean, basically, think about this. If I tell you I'm going to be meeting you at in front of Columbine Hall in 2 hours and in 2.31 hours, when am I actually coming? Sometime between 2 and 3 hours, right? I see. Okay. You'll just get there in 2 hours and make sure you just wait for me until I come, right? Do you understand do you understand the issue? The problem is, when you're dealing with real numbers, you want to talk about decimals, because that's, we're dealing with the decimal system. And so if you use anything else but things that can be turned into a decimal, I mean, it's very easy to actually, by the way, in case you're actually wondering, since I just talked about it, let's put it on the side here out of curiosity. 2.31 hours. Do you know how to compute it? How many minutes? You're looking at 2 hours and 0.31 out of 60 minutes. Does that make sense? Everybody understands why that's the case? Oh, an hour is 60 minutes. So I'm taking 0.31 of an hour and divide that by 60 minutes. Actually, times 60. Nobody said anything. He was wondering. Of course, no, he says, I see how it is. I'm joking. Is this making sense? Okay. So now coming back to our radians. These are basically the 5 angles we deal with. Why? Well, these are basically the fundamental 5 angles. And these are all going to be in the first quadrant. Well, technically. Right, because 0 is actually on the y-axis, so on the x-axis, so it could be technically interpreted as fourth quadrant. But anyway, these are basically all first quadrant angles, and based on the lovely trigonometric circle and symmetry, we can basically come up with any sine, cosine, tangent, or whatever you want to think of any other angle involving these in the other sides. Okay, and we'll look at it over quickly. Actually, I can just briefly say that. Look at the trigonometric circle. First quadrant. What are the signs of cosine and sine? Positive and positive. Does that make sense? Why? Because both x and y are positive. Go to the second quadrant. What are the signs? SIGN and not SIN. Negative for cosine, positive for sine. Does that make sense? Everybody understands why? Yeah? Okay, one thing, if you don't necessarily see it, just always keep in mind that that's associated with x and y. Second quadrant, x is negative, y is positive, hence that. Third quadrant, both x and y are negative, so they're both negative. Fourth quadrant, positive and negative. So now if I ask you, what is the sign of tangent in the third quadrant? Positive. Why positive?
Both x and y are negative.
Yeah.
Remember what tangent is? It's sine divided by cosine. If they're both negative, that makes it positive. Does that make sense? Okay, so now these are the 5 angles, and we have 5 numbers associated with these angles. And the numbers are as follows. There's 0, 1/2, square root of 2 over 2, square root of 3 over 2, and 1. Now, if you want them to be learned in an easier fashion, a student of mine, I think it was like a year ago or so, came up with this idea, which I actually found very interesting. You can also think about them as 0 over 2, or better yet, the square root of 0 over 2, the square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, and square root of 4 over 2. They're all the same numbers, right? Square root of 0 is 0, this is 0, square root of 1 is 1, so you end up with 1/2. Come back to the last, square root of 4 is 2, 2 over 2 is 1. Does that make sense? Yeah? Okay, so now here comes the fun part. 0, pi over 6, pi over 4, pi over 3, pi halves. Sine of theta, cosine of theta. So, as I said, the one thing I always remember is that sine of 0 is 0. Can you tell me what sine of pi over 6 is? 1/2. Keep in mind, think about the trigonometric circle. Both sine and cosine are positive, right? If I start at 0 and I'm going towards something, the idea is between 0 and pi over 2, both sine of theta ends up being increasing, cosine of theta ends up being decreasing. But that's not necessarily the important part. The idea is all of those numbers are going to be associated with the same sequence of degrees. The only difference is, are they going to be an increasing fashion or a decreasing fashion? Okay? So as a consequence, if that is my sequence, I'm going to have 1/2, I'm going to have square root of 2 over 2, square root of 3 over 2, and 1. Does that make sense? On the other side, cosine of 0 is 1. Again, cosine is positive. Actually, moreover, cosine and sine are bounded between -1 and 1. It can't be higher than 1, so it's got to start decreasing, right? So, root 3 over 2, root 2 over 2, 1/2, and 0. Is this making sense? Notice I didn't actually write tangent. And normally I don't actually bother to remember all the values of tangent, because the way I always deal with tangents is sine over cosine. So if I'm asked to find out what tangent of pi over 6 is, for instance, well, I think about what sine is, I think about what cosine is, will be 1/2 over the square root of 3 over 2. So it's just 1 over the square root of 3. Right? Now if you look at the table, that's actually written as square root of 3 over 3, because we usually like to rationalize denominators. But anyway, that's the point. Is that making sense? Yeah? Okay, so let's play a game. What is sine of 7 pi over 3? And since I said let's play a game, that means you get to play. What is it? Square root of 3 over 2? Which quadrant are we in?
First quadrant.
We are in the first quadrant. Why are we in the first quadrant? This is just pi over 3 plus 6 pi over 3, which is pi over 3 plus 2 pi. Sorry, I tricked you. I didn't say I can't trick you, I just said let's play a game. Is this making sense? Okay, how about sine of 7 pi over 6? Negative 1/2. Why negative 1/2? What do we have to acknowledge? We're in the third quadrant because it's pi plus stuff. Question is, what's the stuff? Pi over 6, right? What is sine of pi over 6? 1/2, which means I'm going to have minus 1/2. Everybody sees how this works? Yes.
How do you figure out which quadrant we're in?
Well, think about quadrants increased by pi over 2, right? So, if you think about this, you're looking at pi plus pi over 6. Right? Which means it pushes you into the third quadrant. Have from 0 to pi over 2, you're in the first. From pi over 2 to pi, you're in the second. Pi to 3 pi over 2, you're in the third. 3 pi over 2 to 2 pi, you're in the fourth. Is that making sense? I said let's not talk about degrees, but if you think about degrees for a second, pi is 180 degrees, which means you're actually going to be crossing the x-axis as soon as you add a little more to it. Is that making sense? Now, usually when I teach pre-calculus and I talk about this, and later on I guess when I teach calculus and I do reviews, I usually tell students that there is really no one particular formula in which you want to play with these. You know, to some extent it's whatever people like to do. I personally don't really want to memorize a bunch of numbers, and so I kind of, if I need to find something, I usually just try and find it in my head. You know, like for instance, I start with sine of 0 equals 0, and I'm being very honest here. So I start with sine of 0 equals 0, and then I basically try and figure out, you know, where I'm at, in what situation I'm really at. Now, if you don't necessarily feel confident with that, or you don't necessarily want to do that approach, and you want to actually just, you know, memorize the numbers, you can go ahead and do that as well. You know, it's kind of entirely up to you. I personally don't really like memorization in general, so. Okay, how about secant of 5 pi over 6? Bless you. Sure.
Oh, that much just
This is where things might actually look a little more messy, right? So the question is, how do we get to it? Well, it's a lot simpler than, if you are in doubt, like the previous two seem to be more simple than this one, right? Because they were kind of like multiples of pi and so forth. So let's draw a circle and figure out where we are. By the way, the answer should be negative. Keep in mind, if it involves square root of 2, it is divided by 4. Is everybody understanding this? Do you understand why this is the case? Remember our values. Where would square root of 2 come into play? Both cosine and sine are square root of 2 over 2 at pi over 4, right? Which means at any point if the angle is divided by 4, you're looking at some sort of a square root of 2 over 2, right? And whatever the sign is, wherever you're actually at. Does that make sense? So if it's not divided by 4, there shouldn't be any square root of 2's. Is that pretty clear? Okay. So now coming back here. Where is 5 pi over 6? Quadrant 2, right here. This angle is pi over 6. Does that make sense? Yes? Okay. So then what is secant of 5 pi over 6? Square root of 3? Keep in mind, secant is 1 over cosine. Right? So this is the same angle as if I look at cosine of pi over 6. Right? Come back up, if you don't remember, what's cosine of pi over 6? What am I writing there? I don't know why I'm writing there. I was thinking about for some reason I was stuck. I was gonna ask you about cotangent, and then I switched to secant, and so for some reason I kind of got stuck with just the actual square root.
Is it also negative?
Why is it negative?
Even if it was 1 over cosine.
So again, keep in mind what cosine and sine are, right? The values of cosine are negative in the second and the third quadrant, and positive in the first and the fourth, right? Does that make sense? And so, okay, about cotangent of, what should we do? Let's be creative. Negative 3 pi over 4. Oh, over 4, that's not creative. Oh, okay. Since I gave you the cheat sheet now. This is really too boring. Is it just 1?
Yeah.
Not creative, right?
Show us how I'm lost. No idea.
Which part?
The whole thing.
Where would you draw them on a circle?
Well, what does it mean to have a negative sign? You go the opposite way. So if I draw my lovely circle here, negative 3 pi over 4 will be right here. Well, think about pi over 4, right? So if you want to think about degrees or you want to think about radians, if I actually just look at the first quadrant, pi over 4 happens to be half of that, right? Pi over 6 is somewhere here, pi over 3 is somewhere there, right? It might not necessarily be obvious. This arc and that arc and this arc are all the same, right? You basically take 90 degrees or pi over 2 and divide it into 3's, right? Now pi over 4 is the middle of that, right? What is 3 pi over 4? Well, there's two ways you can think about it. You can either think about it as pi minus pi over 4, or you can think about it as pi over 4 plus pi over 2. Okay? Is everybody seeing that you get at the same place?
Yeah.
Yeah? Okay, so that should basically tell us that we're in the so-called second quadrant going the wrong direction, right? Or third quadrant if you actually think about the right direction. But forget about the minus. The fact that it's a minus, it just means we're going in the opposite direction, right? So that means this pi over 2 means I'm passing this point, and then I have to add pi over 4, right? This one means I'm switching all the way coming here, and then I have to come back a pi over 4, right? Does that make sense? Okay, we're there. What is tangent of... What is cotangent or tangent of negative 3 pi over 4? Well, they're both 1, right? Does that make sense? Again, the idea is, if you look at pi over 4s, you're going to be looking at the same values for sine and cosine. So if I ask you for tangent or cotangent of any angle involving a 4, it'll be either minus 1 or 1, depending on which quadrant you're in. Does that make sense? Yeah? Okay. Okay. Yes?
Is it too early to ask to be one of the inverse functions?
Well, let's see. Let's come back to it and see. Oh wow, I'm really going like a snail pace through this. Okay, I'm guessing now then there shouldn't be any point in spending time on this. Is everybody understanding how these work now? Okay. 20. 21. Okay. One of the things that I wanted to point out here, because I've seen this on a lot of tests, and I figured I'll be nice to you and actually give you half the points for this. What are the first 3 words of this particular sentence? Find 2 values. I'm thinking about half the class found 1 value. Do I need to spend more time?
No.
Okay. Move on. 22. Graphs of trigonometric functions. First of all, what is the amplitude?
That's how high it is.
Technically, it's half how high it is.
Oh, yeah.
The negative does not play a role in the amplitude. The negative just means, remember back talking about functions, the negative just means that you're actually flipping the graph on the y-axis. It'll still have the same height. So when you're dealing with amplitudes, you're only looking at the absolute value of the number in front of the trigonometric function. Right? So the amplitude is always located in front of the trigonometric function. Minus plays no role, so it's going to be just whatever number it's there. Okay? Is that making sense? Do I need to go back to y equals a times sine of bx plus c? Forget about the c, since I guess we're not actually using that for this particular problem. Let's make it a little simpler. What is a times sine of bx? What is the amplitude? What is it? Absolute value of a. What is the period? It doesn't matter which one it is. It is b. Oh, sorry. I'm saying that wrong. 2 pi divided by b. Does this make sense? Everybody remembers this?
Yes.
Now you remember. Well, that's still a bonus. At least you remember, and it's not like now I know. Again, and this is basically what I was basically saying, okay? If you miss the trigonometric functions because you don't necessarily remember things, but as soon as you look at them, they kind of jump at you, versus looking at this and say, I've never seen this in my entire life, that's when you basically have to realize the fact that later on we're not going to come back to this more or less. I mean, I might say a word here and there, and I'm going at a very slow pace right now, and I've kind of said it, and it's probably not very, you probably don't believe me because you haven't seen me go faster, but trust me, once we start with the calculus concepts as they are quite complicated. There's no way I'm going to actually have the time to go back and review all the concepts that you may or may not necessarily have at that point, like pre-calculus concepts, algebra concepts, and everything else, because we just don't have the time. Which again, probably might not necessarily seem like that, considering I'm, goofing around every single little comma over here. Is this making sense? Okay, so coming back to this, we're looking at the graph. Any point spending time on the graph? That's the graph. Okay. 23. The one thing you have to acknowledge here, and there's two types of graphs here, so I can tell you this much. You'll always have a type of this, for this particular problems, you'll either have this, these two graphs look very much the same, these two don't. If you chose the wrong of these, I gave you half the credit. If you chose either of the B or the D, I gave you 0 credit. Why? What should jump at you immediately when you see your original function? Absolute value. How can this be the graph of an absolute value function? Moreover, it's an absolute value function. Think about what the graph looks like. It looks like a V, right? There should be a point in which if you fold the graph in two, it looks the same, right? That said, that's basically what we're going to be looking at. Okay, either that or this. What is the difference between these two? Period. The period. Right? Does that make sense? Okay, move on. 24, 25, skip. 26, 27, 28. And I guess these are the last three problems we're going to talk about anyway. Inverse trigonometric functions. And these seem to be a really big problem. Let's come back to the graphs. Y equals sine of x. Do you remember what the graph looks like?
Yes.
Right? Again, sine of 0, 0. I know they're wavy because sine of 0, 0, it has to be in that fashion. Is that making sense? Okay, so now if I come over here, y equals sine inverse of x is equivalent to saying x is equal to sine of y, right? That's actually how we define inverse any functions. We always define them based on the fact that we're taking the opposite of it, right? The minus 1, by the way, doesn't mean 1 over. I'm hoping everybody knows that, because otherwise sine inverse would be just cosecant. So why would we call it something else? Yeah? Okay. What's wrong with the picture on the right hand side? When do I have inverses? When my function is 1 to 1. Right? Do you remember what a 1 to 1 function is? The actual definition of a 1 to 1 function is that for each value of y, there corresponds one and only one value of x. Okay? Or I guess it would be at most 1, because there are values of y for which there is no value of x, like 2. Find me an x for which sine of x is equal to 2. Also, graphically speaking, and that's actually the simplest way to think about it, is a function is 1 to 1 if it passes the horizontal line test. A function or an expression is a function if it satisfies the vertical line test, right? Everybody remembers that? Yeah. So if it satisfies the horizontal line test, then it's a 1 to 1 function. Well, would this be a 1 to 1 function? Everybody, I'm hoping, sees that it doesn't pass the horizontal line test, right? It actually will cross the graph in an infinite number of places if I start crossing it out. Which means this only makes sense if I put some sort of a restriction on x. What should the restriction be? Or I guess better yet on y, right? Since this is defined in this fashion. So what should the restrictions on y be for me to actually talk about a one-to-one function? And the convention is in general that we want to focus on an interval involving 0. Why? Because it makes things a little simpler. That's not the only way to do it, but that's basically the standard way of doing it, and that's the only way you actually see it in textbooks. You know, it's kind of like a convention that it's agreed upon. If I focus on myself on this particular picture, I will have a one-to-one function, right? Which means I can come back here and say that y actually has to be in the interval minus pi over 2 and pi over 2. Does that make sense? So if I come back to my problems over here, and I'm asked what is the sine inverse of minus 1/2? Okay, so let's come back here and say sine inverse of minus 1/2 is equal to some value of y, which I don't know what it is, right? This is equivalent to saying sine of y is equal to minus 1/2. For what value of y is sine minus 1/2? Okay? Well, as it turns out, remember what sine is, right? It's corresponding to the value of y, which means sine is negative in the third and the fourth quadrant, right? So I would technically have a wide variety of solutions, right? If only I'm focusing on this particular picture over here, right? It'll end up that y is equal to 7 pi over 6 or 11 pi over 6. Does that make sense? Yes? But what's wrong here, based on what I have there in, I guess, orange? It is not there, right? Neither of these two values are there. How can I make them be there? I have to pick minus pi over 6. Does that make sense? Yes? Okay. So that being said, cosine inverse of x is equal to y, which is equivalent to y equal to x equals cosine of y. Can you tell me what the restrictions on y would be? Keep in mind what we're actually asking. We're asking for the restrictions on y. Look where y shows up. It's cosine of y. Right? Moreover, remember going up. Remember when going up, what the conditions on y were here. Why did we choose this particular interval? To make our function one-to-one. How should we choose our interval to make our function one-to-one for cosine? Should I draw a picture?
Yeah.
What is the graph of cosine? Starts at 1. It has to go down, right? So okay, my graphing skills are really excellent today. Everybody sees that? So what should I pick? Zero to pi, right? Why? Because that's the place where my function is one-to-one, right? Again, I could have chosen it here or there or anywhere else, but why would I choose 101 pi's to 102 pi's? You know, why not choose 0 so you make your life a lot simpler? Is that making sense?
Yeah.
Okay. Tangent inverse of x is equal to y is equivalent to saying x is equal to tangent of y. What are the conditions and why? Not quite. Remember what the period of pi is. No, the period of tangent is. How did I get that? What's the graph of tangent? No idea what it is. Right? This is minus pi over 2. This is pi over 2. Again, nobody's stopping me from technically saying I can choose pi over 2 to 3 pi over 2, but really do I want to go, all that far away? And so the whole point is we want to choose 0, and so this is what we're actually looking at. Does that make sense? Now, because both minus pi over 2 and pi over 2 are tangents, are vertical asymptotes, they can't be part of your interval, right? That's why I actually use parentheses and not brackets. Does that make sense? Okay, so that being said, if you come back here, 27 was a cosine inverse, and 28 was a tangent inverse. I will not worry about cosecant or secant inverse. They're always really screwed up the way you describe them or you define them, and actually different textbooks have different things. However, it's very easy to define a cosecant inverse. Right? Cotangent inverse. Everybody knows what the cotangent inverse would be defined on? What the interval? What was the interval? What was the difference between sine and cosine? We went from minus pi over 2 to pi over 2 to 0 to pi. So 0 to pi. Remember, they're co-functions. They happen with a shift of a pi over 2. I told you that once. Keep that in mind in general. That's something that you can always use to your advantage.